In this recording, we will discuss script Mfiles. These are short MATLAB programs that you will write in order to solve the MATLAB homework problems that you have been assigned. In another video, we'll discuss function Mfiles. A different kind of object to handle a different kind of thing. But for this video only, we will discuss only script Mfiles. We will describe how to write them, how to structure them via cells, how to make them more user-friendly by incorporating comments, and finally, how to publish them in order to give you the capability to present to your instructor a finished product that they will be able to read. So these are the three main features of script Mfiles that we will focus on: how to organize them by cells, how to incorporate comments to make them useful, and how to publish them so that you can transmit them to somebody else. Now, you already know how to issue simple MATLAB instructions at the command prompt. So the command prompt is, of course, the double carets that you see in the MATLAB command window, the basic MATLAB window in which you type your instructions. So, for example, if you were to type at the double caret, say sims xy, colon, and then solve x squared plus y squared equal 1, comma, x plus y equals 0, then basically you're asking MATLAB to simultaneously solve the two equations, x squared plus y squared equal 1, x plus y equals 0. And the common solutions are, of course, the points of intersection of the two curves represented by those two equations, the first of which is the unit circle, and the second of which is a 135-degree line through the origin. Of course, those two curves intersect in 2 points. There's one, there's the other, and if you'd like the coordinates of those 2 points, just type in these instructions to MATLAB. Here's a second example. If at the command prompt you put in a vector, capital X, starting at minus 2 pi, with step size 0.1 up to 2 pi, then you can use that vector to plot x sine x. And if you issue that command, of course, you will get the curve, the sinusoidal curve on the interval minus 2 pi pi. So for x between minus 2 pi and 2 pi, that command will plot sine x on that interval. Let's consider now a third example. Suppose at our input double caret we type sims t, y, y of t, making all those symbolic. And now we issue the command dsolve of the following differential equation, diff y plus 1 over t times y equals, with a double equal sign, because that's the syntax for dsolve, sine t, and also y of pi of pi equals, again with double, 0. Then what we have done is issue the MATLAB commands to solve the initial value problem, y prime plus 1 over ty equals sine t, y of pi equals 0. And MATLAB can solve that problem rather easily, and I'll write down the solution in a moment. But suppose we want to do something with that solution. We want to graph it or evaluate it at some points, then we have to issue more commands. For example, if we want to graph it, then we should do the following. Say solution, SOLN, equals, and this, again, I won't write it again, but right here. So now the output from the desolve command will be the function, which, as I said, I'll write down momentarily. I called it now solution. And then if we type easyplot solution, the solution function will be graph plotted by MATLAB. Now here is the actual solution that comes out. It's sine t minus t cosine t minus pi over t. And that function clearly has a singularity at t equals 0, and it also it satisfies that its value at pi is 0. You see that easily. This, if you put t equal pi, you get 0 here, plus pi there, minus pi there. Now, easyplot decides to plot that function on an interval which contains 0. And so the graph you get is not really the one you are interested in, and so you really need to issue yet another command of the form, let's say, easyplot solution, let's say on the interval pi, pi over 2 to, say, 4 pi. And then you get a much better realization of the graph of the solution with this, which is includes the point pi in the domain. So the point is that sometimes, in order to solve a particular problem, you have to issue a sequence of commands, maybe not just one, but several commands in a row in order to deal with your problem. And if that is the case, it's useful to bundle all the commands together in a single file, which you can then edit or augment and execute multiple times in order to refine your work and proceed more effectively. Now, to illustrate this, I am going to build an Mfile for a very specific problem. We're going to look at problem 5 in problem set A of the MATLAB book, Differential Equations with MATLAB. This will provide a nice illustration for us as to how to build an Mfile to solve a specific problem. It will be a sequence of commands broken into cells with copious comments, and then finally I'll show you how to publish it. Okay, here it is, reproduced directly from the Differential Equations book, problem set A, which is practice with Mathematica. But as it says here, for the purposes of this video, only problem 5 is reproduced. So here's problem 5 right here. And it asks you to plot these two functions, x to the 8 and 4 to the x, on the same graph, and determine how many times those graphs intersect. And you're given a hint. You'll probably have to make several plots using various intervals in order to find all the intersection points. After you've done that, you're asked to find the values of the points of intersection using the findRoot command. Okay, so now we're going to build a MATLAB script Mfile in order to solve this problem. Okay, here's our script Mfile for solving problem 5 in problem set A. As you will see, it is a rather short program, very well commented, segmented into cells for ease of presentation and debugging, and largely self-contained, except that when we execute it, you'll see several figure windows pop up, which contain the graphs that result from our plotting commands. Finally, at the end of the execution, we'll see how to publish it. So let's look more carefully now. Here's the Mfile. You will see there are two kinds of lines. There are lines that begin with a %sign. Those are comments. And then there are MATLAB commands. You'll also note that some of the commented lines have a double percent sign. Those delineate the beginning of a new cell. So here's one cell. If you'll note, if you click in a cell, it becomes slightly darker. It's a little hard to see, but in alternating, you see the darkness of the cell that you're in. Okay, so I'm now in the first cell, which contains the statement of the problem, namely to plot the two functions, x to the 8th and 4 to the x, on the same graph, and find the points of intersection using the find root command. So the first thing we do is just do a little clean house. We clear all the variables, close all the graphs, and if I click up here on the run section, it actually does that. So now let's pass down to the second cell, which is labeled the solution to problem set A number 5. We begin, notice the comment, we begin by graphing x to the 8th and 4 to the x on the interval minus 10, 10. These lines, of course, those that begin with a percent sign or comments, they're not evaluated by MATLAB. But now it's followed by a bunch of MATLAB commands. An easy plot of the first graph, x to the 8th, on the interval in question, minus 10, 10. We issue the hold on command so that when we then plot 4 to the x, it'll be plotted on the same graph over the same interval. And I titled the figure Figure 1, so let's see what happens. There's the graph. Okay, here's the two graphs, one like that and one like this. You should be able to see that this is x to the 8th and this is 4 to the x. It's hard to see what's going on between minus 2 and 2. They could intersect there. They clearly don't intersect to the left of minus 2. 4 to the x is going to 0. X to the 8th is going to infinity. To the right of 2, not so clear. Okay. And so that's the comments here. There may be points of intersection between minus 2 and 2, but none between 2 and 10, nor between minus 10 and minus 2. So it seems. Let's plot on minus 2, 2 to get a clearer picture. So I issue a new figure command, which brings up a new graphics window. And I'm plotting the same two graphs, but this time only on the interval minus 2, 2. I labeled it figure 2. And let's see what results. I run the section. And now we see what's happening between minus 2 and 2. Here's x to the 8th. Here's 4 to the x. And there's 2 points of intersection. I don't know, this is a little less than minus 1. And this is somewhere, I don't know, 1.2 or so. We start a new cell, labeled it number 5 continued. And again, we see there's 1 point of intersection at about minus 0.9 and another near 1.2. Are there other points of intersection? So let's bring up the graph again. Right? As we decided, there's none over here, but there could be to the right. Depends on the growth of those two functions. So here's the words. To the left of 0, 4 to the x is less than 1. In fact, it tends to 0, whereas x to the 8th goes off to plus infinity as x is approaching minus infinity, so there are no points of intersection. On the other hand, both x to the 8th and 4 to the x go to infinity as x goes to infinity. So the graphs may intersect again to the right of 2. Let's check. So bringing up a new figure, and I'm easy plotting again the two graphs, this time on the interval 10 to 20, and I restricted the axes of the x variable is between 10 and 20, but y is between 0, and I cut it off at 10 to the 10th. And you'll see in a second when I evaluate this cell, I clicked in it, I run it, and sure enough, the graphs do intersect again. Out here, it looks like around x equals 16. Could they intersect yet again? In fact, not, and that is explained here. We see that the graphs cross near x equals 16. Using calculus, you can show that the graphs never cross again, for example, by taking logarithms. So in fact, we have found all the points of intersection. There are 3 of them. There was one near -1, one around 1.2, and one out at 16. So now we're going to finally use the F0 command to find these points of intersection numerically. So I define a function, which we call func, using the at symbol, which is the preferred method for defining functions, and it's just the difference of the two x to the 8th and 4 to the x. And then I apply F0 to that function, and I do it 3 times near each of the 3 points where I've approximately located zeros. Let's do it. Run the section. Now what? I have to look in the MATLAB window to see the output. And here it is. Right, there's the function, and so there's one at -0.8613, another one at 1.2396, and a third one at 16. Notice these are decimals, 5 decimal places, and so in principle they are probably just approximations to the actual value, which could be irrational or even transcendental. We can check in this last cell by plugging them in to the function. So I'll evaluate each of the roots to the power 8, subtract from it 4 to the root, and see what we get. So I'm clicking here and running the section. And again, I have to bring up the MATLAB command window. And here are the 3 answers. This is basically 10 to the -16th, 10 to the -16th, -15th, essentially 0. And the last one actually is 0. And now if we go back to the file, we see that R1 and R2 very nearly satisfy the equation, as we expect for very accurate numerical solutions. And then in fact the third one, 16, actually satisfies the equation, which I've verified right here. 16 to the 8th actually is 4 to the 16th. That concludes our presentation of this MATLAB script Mfile that we developed for handling the solution to problem 5 and problem set A. You'll notice that it's organized with cells and that there are copious comments. And finally, we need to see how to publish this gadget, and I will do that next. In order to publish the file, we look up here at the top and click on the Publish tab. And over here on the right, under Publish, first thing to do is to click on Edit Publishing Options. And these 2 are the key features, the output file format and the output folder. It's already set to PDF. You could change it to one of these others like HTML or a Word document. I prefer PDF. Let's leave it at PDF, and you should set the folder where you'd like it to appear. Once you've got those 2, you just click Publish. And it basically runs the file. And be a little patient. It brings up a PDF inside Acrobat Reader, and there it is. Notice it generates a table of contents from each of the cells. Those are the titles of the cells, and here's your document, PDF document, which contains the comments, the commands, and the output. Right? Our output was graphics in most instances. And later on we had some non-graphical output. Let's just check that it's there. There it is. Right? The results of running F0. So this is now, as I said, a PDF. You can save it and email it, whatever you would like to do. You could print it, turn it into your instructor. That concludes our discussion of Mfiles, how to write them and organize them and publish them. Here are a few more comments to conclude. For more information on Mfiles, you should take a look at chapters 4 and 9 of the MATLAB book, Differential Equations with MATLAB. There you will find various debugging techniques, more information on publish and alternative methods for rendering your Mfiles, more suggestions concerning MATLAB syntax, some graphics hints, and finally some troubleshooting techniques.